Hi, this short lecture is an exploration of a practical matter. So far, we've been using this force law, so the magnetic force on a moving electric charge depends on how the charge is moving relative to some background magnetic field, right? But we rarely experiment or have basic physical situations. We rarely have a situation where we can watch a little charged particle in some background magnetic field, right? This is rare. What we have instead, usually, is we have a wire, and these moving charges are moving along the wire as current. Right? So this is normally what we talk about is current. And if we have in the background some magnetic field, then this magnetic field can push or pull on this wire, right? It can deflect the wire with a magnetic force. And that's what I want to talk about now, is how do we understand the magnetic force on a current carrying wire. All right. So let's have a very concrete, very elementary starting point, though. Let's imagine that we have some uniform field that is pointed out at us. And in this, let's put a straight section of wire. All right. Let's imagine there is a current I. So that means I have these little charges that are drifting along. So each of these little charges has a drift velocity. And the drift velocity, we're going to assume that every particle in here that's moving as conducting charge, assume VD is same for every conduction charge. So here's our problem. We have this wire, and if I imagine that there is a section of wire, say of L long, right? I'm going to have a bunch of charges in here that are each moving towards, for example, towards the right, if the current is towards the right. And there's going to be a magnetic force on each of those charges. And we'll say that the force on this section of wire is just the combined force of, so I drew 1, 2, 3, 4, 5, 6, 7 little positive charges. So the force on the wire is just the sum of the magnetic forces on each of the 7 little charges that are moving as conduction current at the speed v sub d, the drift velocity, right? So if that's the case, then what I need to do is just figure out what is the net conduction charge that's moving, right? Let's figure out how much charge is in there. So the way I find that out is I think in terms of the current. So the current is the charge per time, right? It's actually the derivative. It's dq by dt. But we're imagining this to be kind of steady. So we're going to say that there is a certain amount of charge that passes by any sort of place on the wire in a certain amount of time t, right? That's what current means. And I want to know how much charge sits in there. So if each of the charges is moving at the drift velocity, then what I can say is if I start a stopwatch, right? I start a stopwatch when this charge crosses this threshold. What I'm going to do is I'm going to wait, I'm going to count up how much time it takes before this charge, which is at the distance L back from this first charge, I'll just say that the amount of time it takes for this last charge to make it across our threshold and be counted in the total charge, that's just the length traversed by the drift velocity, right? That's how much time I have to wait before this last charge comes and makes it past this dashed line, right? So let's go and put this up in the current. So the current is Q over T, right? I wrote it here. And the amount of time I have to wait for that to charge, all those 7 charges to be counted, is L over VD. So if I divide by T, that's Q VD over L, right? So that's the current. So what's interesting is now to think about what is the magnetic force on all of this conduction charge. So the magnetic force on all that conduction charge, which is going to be the force on this section of wire, is just the amount of charge that's moving times the drift velocity, vector cross product with the magnetic field, right? But an interesting thing I can do is I can realize this interesting connection. So the right-hand side, right over here, QVD over L, is equal to I. So if I multiply the L up against the I get IL equals QVD. And I'm going to vectorize this. So current is a scalar, but this length can be known as a vector if I match it with the direction in which the current is flowing. So I'm going to erase the fact that L was just a length of a section of wire, and I'm actually going to identify L as a vector that represents the direction of the wire carrying the current. So that matches each of these little V sub D arrows, the little drift velocity vectors. So I'm going to say that I times the L vector is equal to Q times the drift velocity vector, because the L vector has the same direction as the drift velocity. The L vector is the length of the wire, but the direction of the current, right? So I'm going to replace IL for Q times V sub D. So that is, oops, I forgot a vector symbol. So there is a magnetic force on a total charge Q that's moving with drift velocity V sub D, but instead I'm going to identify that total charge Q and drift velocity V sub D as I times L. There's a current on the wire where the wire is of a certain length with where the current specifies the direction. And I'll finish with the vector cross product with B. And this is a very useful relationship. This is how you design electric motors. Imagine having a magnet. So let's say that I've got a magnet Here's the North Pole and the South Pole. And here's another magnet, and I'll just organize it to be South Pole, North Pole like this. And what this means is that I have a magnetic field, which is going to look like this between the poles, right? And actually you can draw the other field lines, but I only care about in the poles. And if I was able to organize a situation where I have a circuit of some sort, where I have a current, then what this equation says is if I have a current and I have that current in a magnetic field, then on the lengths of the current, there's going to be force, mechanical force, right? Force that accelerates, force that causes motion. Yeah, and so that's how you design an electric motor. And so that's what we'll continue to talk about in some following lecture videos. But this formula right here, this relationship is a nice, useful, practical way to understand the relationship between force and magnetic field. But this is the context of a current carrying wire, or a length of a current carrying wire, right? So it's very practical. Earlier, we started off this way. It's not so practical in everyday applications because it's not very often that you can watch individual electric charges and know their velocities, right? That's more of like an elementary particle experiment. So elementary particle physics, this formula is useful for that. But for very practical situations, right, it's very practical to imagine having electric circuits, right? Voltages that drive currents, and I've got a current on a wire, and if I have a magnet, I have the beginning of a way to convert the electrical energy required to push a current in a resistive circuit, right, into mechanical motion, right? Mechanical energy is the conversion of electrical energy to mechanical energy. And this is one way to do it. It's a practical, useful, utilitarian, modern thing to do.